GCSE Maths Topic by Topic. Today we're going to have a look at probability. What is the probability that tomorrow will be a sunny day? What's the probability that it's going to rain tomorrow? What's the probability that the next child born in the world will be a girl? All these sort of things sort of have chances, and if I were to sort of throw a dice, toss a coin, then we get various probabilities here, and we're going to start having a look at perhaps the meaning of probability. So we could make it really quite simple, and what we could do is we could have what we'll call a likelihood scale. Now, a likelihood scale is from impossible to certain, and somewhere in the middle we're going to have evens. So how about something that's impossible then, that yesterday will be, and today is a Monday, so yesterday will be a Monday. So that's impossible. Something that's even. Tossing a coin is one of the obvious ones. If we toss a coin, then it can land on heads or tails. And other things are certain. Well, one thing I suppose certain in life is death and taxes. So it's certain that someone will die today somewhere in the world. So we've got these sort of probabilities, and we can look at some of these probabilities with things like packs of cards. We can look at things with dice. We can look at things with coins, and I suppose another one that comes up are spinners. So we can have a look at a whole load of these types of things and see if we can predict what they're going to do. And some of them are done with experimental probability, that we actually do get out some cards, we get out some dice, and I need a coin, or maybe we make a spinner. And so we can try and do this, and we can compare with something that we will call our predicted with what we might find we actually get. So let's suppose I take a coin here, one of my awful coins, and I can toss this coin, and this coin can either form as a head or a table. So let's pretend that I throw a coin, and obviously we're going to get either a head or a tail, and that's basically a simple sort of, well, we've got a chance of 1 in 2. But if I throw a coin, here we go, it lands on heads. Next one must be a tails, of course, but unfortunately it was a head. And so this ruins this idea of predicted, because the actual isn't going to be the same. I've thrown 2 coins and both are heads, so therefore probability must be wrong. but it's not, of course, because if we throw this coin enough times, there's 3 heads in a row, and then there's a tail. If I throw this coin enough times, then this will eventually come out as the probability of evens, a 1 to 2. So our actual probability and our predicted probability, they might be different, and this can cause some people a little bit of confusion. Let's take simply a die. It's got 6 sides, so the probability is 1 in 6. Let's have a look. I've got 6 sides. So if we take a die is the singular of dice, I can get a 1, a 2, a 3, a 4, a 5, or a 6. And if I throw this badly, I've scored a 5. If I throw it again, we can score a 2. I'll try and get it where you can see. I've scored a 3. Oh, this is doing really well. I scored a 2 again. I've scored a 3 again. And I've scored a 1. So the probability is that if I throw this, each one should be 1/6. But of course, each time I throw it, this is a mutually exclusive event, and so each time I do it, the chance of doing this is 1 in 6. How about having a baby? Well, this is easy. Well, predicting it is. We've got a choice simply of a boy or a girl. So let's suppose someone has a child and they have first of all a boy. What's the chances of them having a girl? Well, the next time it's still this 1 in 2 chance, and because of that, then they could have 2 boys, like I have, or my sister-in-law's got 2 girls, or like my mother had, a boy and a girl. You can't predict this with a small group. The larger the group, then the easier it is to work out what the probability is going to be. And life is largely based on probabilities. Insurance. We have a look at things like car insurance. You want to insure your car. Well, you don't really want to insure it, but you have to. So you've got to insure your car. If you are a young person, then you're more likely to have a crash than if you're an older, more experienced driver. So premiums are loaded towards the younger people because they are more likely to have a crash. Now, that doesn't mean to say they will. That's just a probability. They are more likely to do this. And when you get very old and your reactions are much slower, then the premiums go back up again, and you are then more likely to have a crash, so therefore the premiums go up. That doesn't mean to say that you will. So we've got other things. Insurance is a common thing, and it doesn't matter what you want, you can insure against virtually anything. You can also go gambling, and gambling here is basically in favour of the house, or the person that's sort of running the betting. What they want to do is, if they've got perhaps a horse in a race and it's a certain win, then the odds are going to be stacked against you. You want to try and make a lot of money, you're not going to make much money. Whereas you might have a horse that doesn't stand a chance and they'll give you quite good odds because they're hoping that you will bet on that one. It will of course lose and they'll get your money. So betting is a system whereby we use probability, but people use the probability there to try and make sure that the odds are going to be stacked in their favour. So it doesn't matter whether we have one thing or another. And we can do a little bit of cheating. Yeah, it's always a little bit of fun when you can do some cheating. So I'm going to roll a die and you're going to bet on getting a 6. Right? So let's see if we can do this. So here we are. We're going to take a die and you're going to guess if you can get a 6 or not. So the probability is 1 in 6. But I could change the odds. I could take a 4-sided dice, and here of course a 6 is impossible. Or I could make life worse. I could take perhaps an 8-sided dice, and then the probability of getting a 6 isn't 1/6, but now it's 1/8. And how the lottery works, we have lots of numbers, and these balls have all got loads of numbers, and the more we've got, the rarer the chance of something happening. So we've got this idea of dice, of coins, of cards, of spinners. And if you don't know anything about packs of cards, then it's probably a good time to sort of get out a pack of cards and have a look at it. When I was a child, yeah, there was this thing called TV. It did come on about 5 o'clock, and then we watched the news, and that was the end of children's TV from 5 o'clock till about 6, children's hour as it was called. And TV shut very early, and we didn't have many channels to choose from. So what do we do all the time? Well, we played cards. And playing cards, we used them a lot. We got used to them. Well, people that write your questions, the examiners, probably still use cards and are used to using them, and you're not. So it's worthwhile playing with cards and being used to the suits, the numbers. We might come back to that later. So what we've got then is to worry about some different sorts of probabilities. We've got risks, which is basically if I've got some sort of risk here, the risk of event, it's going to be equal to the number of trials where we've got this event happens over the total number of trials. And there are people whose job is this, an actuary, someone who would basically spend their life trying to predict whether and the likelihood of something happening is going to be. But for that we've got to know how often something happens. So if you're doing a simple thing like a car crash, you record how many car crashes occur in England in a year. You record the ages of the people. You record, well, as many things as you can. But if we just recorded the ages, then we might find that if we drew a graph of this, then it might look something like this. Here are our young people, and here are our old people, and there are your middle-aged people, the ones with the most experience. And we find that if there's a graph like this, then we can stack the odds here, not in the favour of these people, and perhaps in the favour of those. So probability, the sort of things we live with all day, every day in our lives, and we are asked to try and work out what those probabilities are going to be. So let's do a simple experiment, and for this I've got my little dice tower. So I've got my little dice tower, and I can take some dice. So here I've got a collection of dice, and what I'm going to do is I'm simply going to drop them down in my dice tower. So if I take 6 dice, and I'll try and get one of each colour, and let's have a look at those dice. There we are. There are 6 dice. Then it's likely, if we put those down, that we're going to get one of each. So let's try this. And what have we got? We've got a 6, but we've got another 6. We've got 2 1s, and we've got a 2 and a 3. So this time no 4 or 5 came out. So if we do this enough, we can predict how my dice are going to play and how they're going to go. And sometimes we can try something called a space diagram. Now, a space diagram we're going to use with these 2 dice, and the blue dice here can score either a 1, a 2, a 3, a 4, a 5 or a 6, and my green dice here can either score a 1, a 2, a 3, a 4, a 5 or a 6. I'm not good at getting my lines the right length. And we can work out what is the probability of getting certain combinations. And I'm not going to draw all these out, you could do this yourself, but the probability here is I can get a 2, and there is only one way of getting a 2, and I could also get a 12, and there again is only one way of getting a 12. Whereas if I want to throw an 11, I can get a 6 and I can get a 5, or I could get here a 5 and a 6. So there's 2 ways of doing that. And of getting a 10, well, there's going to be just several ways of getting a 10. I can get a 6 and a 4, a 5 and a 5, or a 4 and a 6. And my 9s, I can get different ways of getting those. And my 8s, I can get more ways of getting those. And my 7s, fairly high probability, it's the most likely number. And then my 6s, and then my 5s, and then my 4s, and my 3s. So we can look at this and say the probability of getting a 1 here is going to, of course, be impossible. Although you may consider some ways that you might be able to do that. Maybe my die gets stuck in the dice tower. Probability of getting a 2 then is just 1 in all that number. So the probability of getting a 2 is going to be 1 in 36, as is going to be 12 is going to be 1 in 36. Whereas my 7s is going to be 6 in 36, or I suppose 1/6. Space diagrams give us a way that we can see and work out what's going on. It's not the only way of trying to do this. We can do this with Venn diagrams, we can do other things. And I'm not going to do Venn diagrams today because I'm going to do that in just one special maths lesson. So how about trying to look at two different events? I could toss a coin, I could throw a die. So we can look at then a probability of these as being mutually exclusive. I could throw 2 dice, and that also is a mutually exclusive event. Or I could throw 1 die twice, and again that is a mutually exclusive event. And if they are mutually exclusive, you can do one, then you could do another one. We come up with here this probability of doing one of these events, we'll call it A, and we've got the probability here of doing another event, and we can call this one B. And I suppose if we try and do this, the probability of this is going to be A or B. And what we do, we take our probability of one and we add it to the probability of the other. And this is called the addition law for mutually exclusive events. So we can work out what we're doing simply by throwing a coin. I'm not doing very well trying to keep them in the frame. Here I've got a head and a 3. and I can do that again. Ready? Yep, did that really well. I managed to even chuck the coin on the floor. And there we are. A head this time and a 1. Throw it up again. I could get a tail and a 4. So each one works independently of the other. So as long as we understand that, then life is easy. Sometimes events aren't mutually exclusive, and when they're not mutually exclusive, then we have to have slightly different rules to try and sort of work out and calculate what's going on. So let's have a look at some things that may not be mutually exclusive. So what sort of things might be mutually exclusive? Well, we can have perhaps a card chosen at random here, and we could have it here being chosen here as perhaps a picture card or a number card, and we've only got lots of those, so choosing one isn't necessarily going to stop one of the other ones being done. Mutually exclusive are the more common ones, and where we can have a lot of fun with some of these are things called tree diagrams. And when we get to tree diagrams, a lot of students have a lot of problems with these, but I find they work out quite easily. And let's have a look at how a tree diagram might work, and what we're going to do is try this out. So what I'm going to do is I'm going to get out my favourite treat tin, bought for me by one of my students, and what we're going to have some green sweets. Let's have 6 of them. We're going to have some red sweets. Let's have 4 of them, and we'll have some orange sweets. Let's have 3 of them. So if we're going to play around with the sweets, we've got 6 and 4, 10 and 3, 13. I've got 13 sweets in all. Let's move those out the way. Now let's do a tree diagram. Got lots of sugar here. I can either have a red sweet, an orange sweet, or a green sweet here. What's the probability of having a red one? Well, that's easy. I've got 4 of them. So the probability is going to be 4 in the 13 sweets we've got. Orange sweets. What's the probability here of orange sweets? Well, this is going to be 3 in 13. And my green sweets here, we've got a probability of 6 out of 13. So let's suppose I've got some sweets and I put them into a bag.
Alexa, stop.
So let's take some sweets and I simply pick them up, and I can't see which one. I'm just going to take one at random, and I've taken a red one. So what was the probability that I could take a red sweet? 4 in 13. So let's put it back. Let's take another sweet. So we could do it a second time. So I'm going to draw out this probability tree again, and because they're the same number of sweets, then for a red one it's still 4 in 13, an orange one it's still 3 in 13, and a green one it's still 6 in 13. And it doesn't matter whether I took a red one first or an orange or a green one, I get again, because we put them back, the same probability. So if I pick up my sweets and I now take one out at random, I've got an orange sweet this time. So my probability here is still 3 in 13. Let's do this experiment though another way. I've got my pile of sweets. I've got exactly the same setup, and of all the mathematical experiments that I do, this is probably my students' favourite. Probability of red here is 4 in 13. The probability of an orange is 3 in 13, and the probability of green is 6 in 13. So what we do, we have a pile of sweets, and what I do is I take one out at random. It's a red one, and the probability of me getting a red sweet was 4 in 13. But now let's see what happens if we do this a second time. How many red sweets have I got? Well, I've eaten one, so I can't have 4, I can only have 3 here. But wait, there aren't 13 sweets anymore, because I've eaten one. Now there are 12. Probability of an orange one, of course, hasn't changed. There are still 3 orange sweets here, but there are still 12 sweets. And green, well, there are 6 out of 12. What's the probability I could take out 2 red ones? Well, let's work this one out. Taking the first red one out is going to be 4 out of 13. Taking the second one out is going to be 3 in 12. And the probability here, we are going to need to multiply these together, and that's going to give me my results. And all we have to do now is work out 4 3s are 12, and if you're not good at 13 12s, this is going to be 156. Let's carry on this idea that instead of perhaps taking a red sweet out, I'll put it back. The good news is I do have a whole sweet tin here, but perhaps the first time we did it we took out an orange. So if we've taken out an orange sweet, then our probability might be different. For my red sweets, we've still got 4, so this is going to be 4 in 12. The orange, though, we're down only to 2 in 12, and my green sweets, I've still got my 6. We could do the same with the green. I didn't take my orange sweet out, but instead I had a green sweet. I like this experiment. Reds, we can see we still have 4 out of 12. Orange, we've got 3 out of 12. And green, we've now got 5 out of 12. So, what's the probability of getting 2 orange? The first time, it's 3 out of 13, and the second time, it's going to be 2 out of 12. And then let's look at the probability here of having 2 green sweets. The first time we take it, it's going to be 6 out of 13. But the second time I take it, it's going to be 5 out of 12. And these are our probabilities. What would happen though if I said, instead of that, I want 2 the same colour? So that means that we can either get 2 reds, which is that path, 2 oranges, which is that path, or 2 greens, which is this path. We've already worked those out. And these are then mutually exclusive events, because I can either take an orange or a red or a green. So we can in fact then add these up. And now we get 12 over 156 plus 6 over 156 plus 30 over 156, which is going to give us here 1848 over 156. Many times when we do this, we do not cancel these and we just leave them as these improper fractions. So probability trees are quite a good way of trying to work out what's going on, these tree diagrams. And either they're going to be the type where things don't change, or they're going to be where you basically remove something and don't replace it. If they're the same, they're quite easy to do, because each of these is going to be basically the same. It's going to be the same however we do it. Whereas if we remove something, then we have to think about these necessarily changing, and this sort of makes life a little bit more sort of interesting to work out, really. So probability is not that difficult, but sometimes we can make it a little bit more fun. So let's suppose instead of taking a fair dice, I take one that is biased, and we can try and see perhaps that instead of being 1/6, then something might be different. So let's look at this dice, and as we sort of throw them, and we can see what we can achieve with these. So let's suppose to start with they're going to be not biased. So I'm going to have my die here, and we've got 1, 2, 3, 4, 5 and 6. Probability of each of these is going to be 1/6. And what we should notice is that if you add all these up, they will equal 1. And they always equal 1. If it doesn't, simply, you know you're wrong. Yeah, it's fair enough how it works. So if I've got a biased die, then we might have our probabilities slightly different. And rather than do them as fractions, I could do them as decimals. 0.1 here, 0.2, 0.1, 0.3. So we might have here, that's 4, 3 is 7, and then 8, 9, and works out again equaling 1. Sometimes in a question what they'll do is they might remove one of these, and they would say to you, what's the value? We add them all up, we take them away from 1, and we have our answer. Another one we might have is to try and work out relative frequency. So let's look at this relative frequency. So relative frequency here could be measured in a few ways. So let's suppose I've got my die here, and we've got it not being biased. 1, 2, 3, 4, 5 and 6. Each one is going to be 1/6. And let's suppose we throw the die 120 times. Well, it won't be in reality, but we could predict that what we're going to have is 120 divided by 1/6, which is going to be 20. So I would predict that if we throw it 120 times, we're going to get 20 of each. In reality, of course, we won't do that. But then we wouldn't expect this to be very different. I might expect some 19s and some 21s, and less often I'd expect 18s and 22s. But I wouldn't expect, if the dice was a fair dice, not biased, to get numbers like 1 or 2. So we can predict the number here by simply dividing by the time. We can work out the number here by taking them away, the probabilities, from 1. And that gives us this simple probability. So we've looked at then basic probability of being things certain and impossible. We've looked at conditional probability, that certain things will happen under particular conditions. We've looked at playing around with these little dice, and we've looked at playing around with simple things like coins and being aware of packs of cards to play around with those. People don't play cards with me. I don't play fair, and therefore they tell me that I cheat. Of course I don't cheat. What I do is I bend the laws of probability a little bit to help, and sometimes knowing what has come up might give you an idea of what will come up. So there we are, some simple ideas about probability. I hope that helps. If it does, then please remember to perhaps like or subscribe, and I will see you next week when we'll have a look at some more maths, GCSE Maths topic by topic. Until then, stay safe. Bye bye.